Yeah, good afternoon, folks. Yeah, like I said, we're looking at more the fine scale water movements, kind of within, not a whole reef, but within a portion of the reef. Moore Reef, situated about 50 kilometres east of Cairns, is a concentric shaped reef. I mean, it has a well-developed reef front and flat that's semi-enclosed or lagoon, dominated by isolated patches of coral. This reef is a high-value tourism site. I mean, it has 3 tourism platforms on it, 2 in the north, 1 in the south. It's also visited by other daytime operators, some weatherboard vessels too. It's reported annually about 20% of the visitors to the Great Barrier Reef go to Moore Reef. How tourists perceive a reef when they go there, or what they want when they go to a reef, is they want lots of high coral cover and abundant fish life. Now, we know disturbance events, they do reduce live coral cover. That can influence, fish abundance and diversity. So the main disturbances we do see at a tourism site level or a reef level, as we all know, high category cyclones, outbreaks of crown of thorn starfish, and of course mass bleaching events. In terms of history of bleaching at Moore Reef, at Reef Magic Cruises Marine World site, this is our weekly, this graph here represents the weekly contribution of, the weekly contribution to the Great Barrier Reef Marine Park Authority's Island Reef Monitoring Program. This program initiated in 2007, and it does show we have bleaching most years, but what it really showcases is those big mass bleaching events of 2016 and 2017. Now, mass bleaching, as we all know, is driven by prolonged thermal stress, which is correlated with higher seawater surface temperatures, breakdown in mixing processes, and most likely flow rates. So how water is moved around a reef at a small scale like tourism sites has a lot to do with the actual configuration of the reef. So the northwest corner of Moore Reef is the reef flat there is divided by several passages. And these passages act as nice little conduits. They protect, they connect the open water to the sheltered reef in behind the lagoon. From previous work done on passages, we know when water flows through the passage, due to the passage, it's restricted in its flow and its current velocity increase. What they term is we get a production of a tidal jet. And this pulls water deep from outside and produces separation points on either side of the mouth of the passage. This is where water movement's a little bit slower. Then on the down current side, you have this production of these mushroom eddy vortexes. Now, tidal jets, they accumulate or retain oceanic plankton and nutrients in the immediate area, and also cause marine life of all scales to aggregate. And this is my prime interest in, it's working. This is my prime interest in reefs, in reef passes. I mean, they are multi-species fish aggregation sites. And my interest in flow patterns is the fact that fish aggregation behaviour changes to different flow patterns. Such obvious behaviours as like foraging and reproduction. And fish assemblages, they change, or fish aggregation assemblages I should say, they change from an hourly to an annual basis. And my interest in flow patterns in this area is to look at them on a seasonal, lunar and tidal scale. So to evaluate flow patterns, I used a couple of instruments. That first one there, that blue one, cable tied in that 32 kilo steel frame, it's called a nephelometer, basically a pressure sensor. Measures water height at 10-minute levels, also temperature and turbidity. Those other 2 more buoyant instruments are connected to that frame. They're versions of current meters. The one in the front, called the lollipop, records current, speed and direction at 1-minute intervals. The one in the back there, it's more refined, records current, speed and direction at 1-second intervals, and also temperature. Now, using an array of these instruments, particularly the more refined ones over about a year or so, I'm able to show you how water is moved within that passage. So these are your kind of traditional rose plots. They're used to plot, wind speed and direction. Now these rose plots here, each bit of the rose does not represent current speed. It actually represents volume of water moved. So for example, water travelling at 0.5 metres a second is going to move 5 times more water than water travelling at 0.1 metres per second. So what we can see is in the middle of the pass here, we get an incredible amount of water pushed through this passage based on pretty well probably tidal flow. The other thing we do see is on the top northwestern corner of it there, we see what marked by those little light blue patches, that water movement slows down. So evidence of like that separation point. So like I say, it looks like we do get tidal jets forming inside that pass. Now the bidirectional flow that we're seeing in most of those current meters, that's probably attributed to tide. But is there a seasonal variation? Does this change on the seasons? Having a look at the 4 plots underneath current there, there's stick plots for the passage. So for each season of the year, I picked 3 current meters in the middle of the pass, 2 on the outer slope, and looked at their mean, basically their mean direction. And there's not a lot of variation in season. And if we are going to get a lot of variation in the season, it's probably going to come from wind. Now there's a reef neighbouring Moore Reef called Arlington Reef. It's got an automated weather station on there. So it records like wind speed and direction at 10-minute intervals. So looking at about 3 years of that data and breaking up into nice seasonal rose plots, what we can see, as we pretty well all know in this region, the wind is predominantly from the southeast, right? With the exception of summer, we get these nice little like northwesterly or strong northwesterly winds. Does the wind influence the current? As you can see from this little regression plot here, winds on the x-axis, currents on the y. There is a weak relationship between current and wind, but it's fairly weak. There's a lot of scattering here. And what this graph is actually looking at is the component of wind and current in their dominant direction. So with wind, that's from the southeast. So that positive value up the right-hand side of the scale there, that's like your really strong southeast winds. So the reciprocal to a southeast is the northwest. So the negative value represents a northwesterly wind. Now, if you're looking at the current on the y-axis, so the positive value is current flowing in through that reef pass. The dominant direction is 195 degrees. The negative value refers to when it's flowing out at 15 degrees. So what this graph kind of says is, basically when you have really strong southeasterly winds, there's always a slight net flow of current into that reef pass. And on northwesterly winds, there's always like a slight outflow of current out through that passage. To have a little bit more deal, like I say, wind has a fairly limited influence, I think, on the water patterns we're looking at. This bottom graph here with the green lines looking at the daily average wind speed. The middle graph is what you want to focus on. That's the daily average current speed from the current meter in the middle of the pass. And you can see it's got these like nice peaks and troughs over that 8-month time series. Now they don't really closely correlate to the wind graph, but if you have a look at the graph on the top, which is moon phase, right, this is a quantitative way of looking at moon phase. So like say the value of 1 is a full moon, 0 is a new moon, so you have a full new moon each month. And you can see our peaks in current speed correspond to the full and the new moon. And actually our maximum current speeds occur about 2 to 3 days before the full or the new moon. So tide tends to be the most dominant influence we're looking at. To look at that in a little bit more detail, using my water height data, I constructed I did my own tidal harmonics analysis and produced a tidal model for the site. Now, basically it's a semi-lonal tidal model. Generally you have 2 highs and 2 lows in a 24-hour period. This model is very similar to the Cairns coastal model in the highs and lows are almost exact in their timing. Now, the animation on the right, that's from that array of current meters there, set up in the pass and the adjacent slope. So what we can see is basically the direction. Just going to see if that arrow was flowing again. Was that video working before or not? Yeah. Oh, it was, okay. Well, basically you would have seen that the direction of the arrows is basically the direction of flow, the length of the arrow reflects speed, and pretty well the arrows change direction based on tide. So when the tide's flooding, it flows in through the passage, and when it's ebbing, it goes out through the passage. what you might have looked at the animation we saw a little bit more is basically the change in tidal direction is not necessarily in sync with the change in tidal amplitude from a high or a low. The change in tidal currents occurs 2 hours in advance. So this graph here, if you're looking at the the left-hand axis there is sea level. So that's the green line. The positive value is a high tide, negative is a low tide. On the opposite y-axis there, we have our current speed. So once again, positive is flooding in, negative is an ebbing tide. And what we want to look at is basically the blue line where it crosses the zero. So where it crosses the zero, it signifies that that's a change from a flood tide to an ebb tide or the other way around. What you'll always notice is it occurs 2 hours in advance to the change in tidal amplitude, or from the peak tidal amplitude, like a high or a low tide. And the other really important thing to notice is the real peaks in current speed, whether they're floods or ebbs, occur almost exactly the same time as that peak high or low amplitude. So when I'm talking about these bodies of water in the past, I think I am talking about two separate bodies of water, a flood body and an ebb body of water. And one way to look at that is to look at their physical attributes. This is the same 3-day time series that we just looked at before, but on that right-hand axis, that blue line is the current speed. Like I say, positives flooding, negatives ebbing. On the opposite axis, we have temperature, and that's marked by the red line. So what you'll notice is when you have your highest flooding tide, your highest current speed, at that same time, you have your lowest temperature. Now, if you're looking at the highest negative value in current speed, then you have your highest temperature value. So, flood bodies of water moving in through the pass are cooler than ebb bodies flowing out, and on average it's around about 0.6 degrees Celsius. So I'm just going to wrap up there. Like I say, in conclusion, the tide is the most dominant influence impacting water movement in through Moore Reef Pass. The spring tides move a lot more water than the neap tides. Wind direction probably is an influence, but it's probably going to be more seen around the neap tides and things like that. Moore Reef Pass does produce tidal jets, although my data was a little bit limited and I didn't have any current meters set up in that back part of the passage to prove if we're getting those mushroom eddies. Thank you. Oh, just before I go, I'd like to say a special thanks to the JCU Marine Geophysics Laboratory. They've been great assistance throughout all my research. Cheers.